Okay, everyone, welcome back to my channel. My name is Ryan Schul. This channel is all about machine learning, artificial intelligence, deep learning, data science. I get into a lot of financial topics as well. Hopefully, you find these teaching sessions and all these tutorials useful and helpful and insightful, and hopefully, it helps you with your learning journey in the data science space. So today, I decided to talk about CNNs. These are convolutional neural networks. RNNs are recurrent neural networks, ANNs are artificial neural networks, and GNNs are graph neural networks. So if you haven't figured it out already, today we're focusing on neural networks, okay? And the pros and cons of all of these. There's not too many cons. They're very powerful, very scalable, up and out, and you can do all kinds of cool, interesting, fun, interactive things with neural networks. If there is one downside, they take a while to run. They can be loaded on a small laptop like mine. A T14 can take a while to converge and to finish these algorithms, to get these algorithms to finish to the end, right? It could take some patience, but the wait is worth the effort, okay? Because they can do some pretty cool stuff. So CNNs basically are used for image classification and object detection. We'll see how that works in just a moment. RNNs are a natural language processing tool, basically for sequential data and text generation. So if you want to predict the next word in a sequence of words, RNNs are great for that. Or for generating text, you can create poems, you can create stories, you can create entire books based on RNNs. If you feed it some information, it can go ahead and write paragraphs or many pages of text for you all on its own, okay? ANNs are great for facial recognition and computer vision, and CNNs are great for social network analysis like Facebook or LinkedIn analysis, graph analysis, things like that, and fraud detection, and we'll see that in just a minute. So make sure that you have these libraries installed. You'll need TensorFlow and GPUs. If you have them, it's going to finish off a lot faster. If not, you can use a CPU. It's just going to take longer to finish. My computer doesn't have any GPUs. It's just not a powerhouse. It's slow, it's cumbersome. I do have a solid state drive, but there's limitations of what you can do. If you have a GPU processor, you can run all of these analytics and all of these neural networks much faster and much cleaner. I just don't have the potential to do that, so I'm going to rely on the CPU to get everything done. Okay, so let's jump in and take a look at what's going on here. So with CNNs, we can actually save time and resources in the analysis that we do around classification and object detection. Okay, so we have a bunch of libraries that we can utilize. We have MobileNet v2 at our disposal, ResNet 50, a few others, right? We have TensorFlow and Keras. These are very helpful. It's going to help us with many of these lifts that I'm about to show you right here. Okay, I have a few images I put in this image folder, and I put it with today's dates. Okay, when I create all these videos, I put the month and then the date. So you would just put your own path down here, whatever path you have. And let me show you the images I have to work with. So I downloaded these from the web yesterday, and if I just click on each one here, I mean, it's kind of obvious what this is, right? This is like some kind of bobcat or wildcat. Maybe it's a lynx. Not exactly sure. This is some animal. That's another animal, probably a moose, right? This is a panda bear, parrot, sports car, truck, boat, plane, and apple, and lemons and limes. Okay, so that's what we're looking at. So everything is in this folder called images, right? And I'm going to get the CNN to loop through all the images in the folder. I say for file name and OS list directory image folder. So if I could do Control F, image folder comes from here. I'm going to create a simple Python loop to go ahead and loop through the operating system list directory image folder. Anything that has an extension of PNG, JPG, or JPEG is going to be detected and analyzed, right? So if you have text files, Word documents, PDFs, it's just going to skip those. So when we loop through each one, and I'm not going to run this just because I had some issues with which environment I was running in. So if I show you over here, now I have the base environment. Let's see, list env. I think it's Anaconda. Anaconda list env. It shows you all the environments that you have in your Anaconda environments. Overall environment. This is the base. Now this thing is going slow too. I guess I'm doing too many things here. Sorry, guys. Sorry, anaconda. What's list environment anaconda, or is that the other one? That's going way too slow. Let me see. Anaconda. Manage environments, conda list environments. Okay, this should show me right here. Way too slow, way too slow. I'm gonna have to restart after the video is done here. Conda environment list. Oh, conda environment list. That's it. So I'll go back here. Conda environment list, and that's so slow too. Okay, maybe we won't go down this rabbit hole anymore, but let me just show you this. Okay, so we have the base. That's the one I'm using. So you can see base right here. If you want to move to a different environment, it's very easy to do that. Conda info environments, and you have more activate, I think. Conda. What was the other one? Sorry. Let me show you one more. Since we went down this rabbit hole, I will go down one more. Just to show you what not to do. Okay, managing anaconda activate. This should show us, right? Stack overflows, decent resource, great conda, activate. Oh, here it is. So it's just activate PP. Okay. So activate. I'm in the base environment. You can see that right now, right? Kind of activate my environment, ENT. And that's going to take another half hour to run. That's just my luck right there. Right. So that's how you activate a different environment. And that is important when you're in Anaconda and Jupyter Notebook, because you can go over here, kernel, change kernel, and you can see this is the base environment. This is my environment. If I switch over here, I can hit select. Then it matches up with this environment right here. That is my environment. And if I do conda, wait, activate base. So why would that go there? That just literally just worked. So sorry. Source by comma create. We have that comma create, comma environment, comma activate. Oh, here it is. There it is. Okay, I'm into my environment now. Now I go back to the base environment. Let me put this over here just for your reference. Okay, and I'll put that at the bottom here. I like to put my notes at the bottom for the most part. And then this thing is skipping around again. I'm not sure why. Let me put one more thing over here. Whoops, I really want it down there. Okay, do that. I'll put that down there. I like to put the end at the end, and then you know everything is finished and final and nothing has been left out. And the other command, let me go back here just for a second. This is worth the time. This is worth the investment. Kind of environment list. Okay. So now you have everything you need. Let me go back here in there. Okay, I know I only say that because I was actually working in the wrong environment today. Then I started installing libraries in the wrong place, and it just caused a lot of time and frustration and confusion and all these great things, right? So big time suck. Don't do that. That's the point here. So let me go back here. So make sure you are in the right environment with here, kernel, change kernel. We are in the my environment. I want this actually in the base. My kernel is the base, and my environment is the other environment. Just make sure that this right here, base syncs up with this. That's all you have to do. Okay, those are the same. So you're good to go. If you get in the wrong environment initially, I got those switched up this morning and caused a lot of headaches. Just don't do that, guys. Please don't do that. So we're looping through all the files in folder. Again, if you take a look at the files, here's the files. We have the links, moose, panda parrot, a couple cars, trucks, boats, planes, and some fruit over here. So each one is listed as the type of object that is detected in the picture and the probability or the certainty, right? Probability with 2 decimal places of what that is. So this says lynx 49% correct, snow leopard 29%, and leopard 3%. And this is a lynx, I think. So that is true. The second one that says, now look, it goes in numerical order. 1 is 10. 10 is this thing. Okay, so the second one we see is object number 2. The 10th is lemons and limes. So it says tennis ball, lemon, cabbage. Tennis ball is close. This is actually a lemon. Number 2 is um, a hearty beast, whatever the heck that is, and a bighorn elk. I don't think any of these are true. It's actually a moose, but it's okay. It's not 100% accurate, but it does a pretty good job. Giant panda, that's number 3. I know that one's right. So we nailed that. Number 4, it's saying is a macaw. I think that's correct. Image 5 is sports car. Yes. 6 is a Jeep or pickup. Oh, that's right. 7 is a speedboat. Yep. 8 is a plane. That's fine. And 9 is an apple. It could be a Granny Smith apple or a hip apple or a bell pepper. We know it's not bell pepper. So 8 plus um, 13 doesn't really add up to 100, right? It's supposed to add up to 100. Over here, we're getting pretty close to 100. There it is. I think this was a glitch over here, but Granny Smith apple, that's what it is. So CNN is working pretty good. It's not perfect, but it's okay for our purposes here. Loading a pre-trained model, scanning images in a folder, pre-processing the image and classifying images, and assign probabilities of items in the image. And that's exactly what we did. So I think we're good here. So the CNN is working. Let's take a look at RNNs. These are recurrent neural networks. These are sequential data patterns capturing a risk of temporal dependencies or patterns over time. These are variants of LSTMs, long short-term memory, and GRUs, and they're commonly used for tasks involving time series data, text, or other sequences. Okay, so word pattern detection, chatbots, what word comes next in a sequence of words, even time series analysis. You can do that for analyzing stock data and things like that. So if we look at TensorFlow and Keras, again, we're leveraging these tools pretty heavily in this teaching lesson. We are going to train, test, and fit this model and look at its ability to detect what is in a string of text. So we have this over here. This is a string of text sample review. The movie was fantastic. I totally loved it. So if I can hit Control F and look for that. So that is the input text. That can be anything, right? We're tokenizing the text right here, adding the text, looking at the padded sequences and making predictions. So we train tested the model. We use it to make predictions, and the model says positive or negative. Down here, the prediction is positive sentiment. Okay, positive. And I'd say that's very positive. That's spot on, right? The movie was fantastic. I totally loved it. So sentiment analysis is one of the potential use cases for RNNs, and word frequency or what comes next in a string of words. Okay, let's look at another example. So we're going to create we're going to leverage a transformer. This is used by LLMs, right? These are very powerful tools for understanding the sequence of words, what comes next in the sequence. If I say 3 or 4 words, you should be able to detect what is going to come next in a normal English language pattern of the words, and that's what the computer is going to do too. Okay, so let's look at an example. We feed this into the text analyzer, the RNN text analyzer. Now we're not looking at images, we're looking at documents. If we go here into my folder, I'll show you all the documents here. Go up one level. Here's my documents. Okay, these are basically Dr. Seuss books, and they're all text files. So Cat in the Hat, this is one right here, and it's all the language from Dr. Seuss. And by the way, the only reason I picked this is because I started looking at books. I looked at Bram Stoker's Dracula. I looked at War of the Worlds, The Great Gatsby, some classic books, and these books are like 500, 600, 700 pages on average, and the model was taking basically forever. I spent a good chunk of yesterday trying to get through a few of these. I didn't even finish one. So I just went to a very simple source of text. You really need like a big processing machine. A T14 laptop, ThinkPad laptop like I have, is just not going to cut through the volume of work here. If you have a cluster of computers with hundreds or thousands of gigs of RAM, you can do it on this laptop that I have. There's no way it's going to happen, guys. So I had to resort to these text files, and just to take simple children's books to be able to allow the RNN processor to scan through it and to finish tasks, right? Otherwise, we'd be sitting here all day. So it goes through all of the elements in this folder right here. Again, they're text files. So if I could do Control F just to look for this again, operating system at path join folder. That is a simple looping task that we're going to do for file paths, we're going to loop through all the files in that folder and then make predictions about the file. So the first thing it's going to do is interpret the text. So it's reading the text and printing the body of text. There's 4 files, 25% done. This is number 2, 50% done. Number 3, 75% done. And number 4, and we finish off 100% done. It creates a tensor. So this is mathematical representation of all the text in those books, and then it shows you the correlations of those texts. So anything on the diagonal, if you know correlation at all, it's always going to be 1.0, right? Because you're correlating the text to itself, it's going to be 1.0. And this is the correlation of one corpus of text to the others, right? So kind of low correlation, but still some positive correlation. These are all Dr. Seuss books, so it's going to be somewhat similar. So let's create a summary like we saw before with the CNN. We can create a summary of what is in the, sorry, was that CNN or RNN? I think that was actually CNN, right? Oh yeah. That was the summary, right? So we created, oh wait, I'm sorry. That was another teaching lesson I did earlier too. I forgot it. Okay, so we read through the body of text and we create the summaries down here. I create some other summaries doing another type of analysis earlier today. So here's the document summary, the name of the text, basically book. This is a text file, but it's a book that we're looking at. The summary is a cat in the hat is a character in Dr. Seuss' book. That's correct. Puppies are Red and Ted and Ned, and they need to go to bed. That's probably correct. I haven't read some of these books in a long time. This is a summary. Every who downhill will like a Christmas a lot. Okay, so that is the Grinch, right? So it's creating a simple summary. One fish, two fish, hop on pop, cat in the hat, so on and so forth. So summaries sound good. Here's a sentiment analysis. Negative, not so much. Dr. Seuss books are not really negative, kind of neutral, right? A little bit nonsense, kind of funny, a little bit positive. So you can see all these books are mostly not negative. There's a couple of negative words, I guess, it detected. Very low though. Most of these are neutral, almost 75% neutral, somewhat positive, and just a couple negative words. I'm not sure how that stuck in there. The Grinch, of all the negativity, I would think that one would score the highest. This actually scores 0. So it's mostly neutral and mostly positive. I mean, the story is positive, that's for sure, but the Grinch was a little bit on the negative side. But anyways, kind of like snuck by us here. We got 0 negativity for that one. So here's recommendations based on the Cat in the Hat. This is a similarity score, cosine similarity, how similar these books are to other books. Hop on Pop, how similar they are to the other Dr. Seuss books, and you can see they're mostly similar. One fish, two fish, and high similarity, and the Grinch, high similarity between Cat in the Hat, One fish, two fish, and Hop on Pop. Okay, so I think we're doing good here. And then what is RNN doing? It's basically loading a pre-trained model, right? So these pre-trained models are important. If you load this model, let me go up and see which ones actually use, because I use a bunch of different ones in different environments. The model was, here, Facebook, BART, language, CNN. So this is actually using a CNN model to do an RNN experiment. That's interesting. Well, I think it worked. I think we got some good results here. So we loaded a pre-trained model. We could train it ourselves, but that would take a lot longer. These pre-trained models are trained over thousands and thousands, probably tens of thousands, maybe even hundreds of thousands of books. So the model knows what to look for. And when you call it and run it, it runs pretty quick and pretty efficient, right? So the pre-trained model is free. It's really the best resource to run with these things. Reading through documents in a folder, we're doing that, creating summarization, producing sentiment analysis, and based on the content of each book, we're making recommendations. So 1, 2, 3, 4, 5, we achieved all 5. So this is mission accomplished, guys. We did it. And this is a source of where I got these books. If you want to go ahead and get your own Dr. Seuss books, you can go here, get these yourself. I don't think I violated any copyright or anything like that. It looks like it's pretty much free, and you can get it right here. Here's the Grinch. And there you go. Just copy and paste that into a text file. That's how I got that. So ANN. So we're halfway through. We did CNNs, we did RNNs. We're going to look at ANNs, and then GNNs is going to be the 4th. So an ANN is an artificial neural network. And we're going to go ahead and load TensorFlow across, like before, sklearn preprocessing, and TensorFlow across again, and cross one more time. Okay, so TensorFlow and cross are the backbones of ANN, CNN, RNN, any kind of neural networks, GNNs. You see that a lot too. So we're going to give what is available to us, or get what's available to us, and get it for free. Now we are looking at people's faces. Again, I copied some faces from online. I did a Google image search and came up with these. This has no sequence or pattern or anything whatsoever. I just found like 12 faces online. 1, 2, 3, 4. Yeah, I got 12. So yeah, this came from Google Images, and I think I just typed in people's faces, and this is what I came up with. Okay, so that is the basis for our analysis, and we got faces there. Well, that's it. That's literally it. So we scanned through this folder, just like we did with the images of the fruit and the boats and the cars, and what was the other thing? The documents, right? The Dr. Seuss documents, same type of concept, image folder path. If I do Control F, we will loop through this. And here's the loop. OS's operating system list directory of getting all the items in this folder, as long as it's a JPEG, PNG, JPEG, JPEG. So if you have other documents, PDFs, text file, Word documents, Excel files, it's just going to ignore those. If it ends with these, it's going to analyze those files. Okay, so we go ahead, scan through that, and let's look at these images, right, and see how accurate it is to make predictions. With the CNN, it was fairly accurate. I think some were questionable, some I would kind of like question that, but I think overall it did a decent job. This is image number 1. It says female. Image number 10. Now remember, it doesn't go from 1 to 2. It goes in this order: 1, 1.0, 1, 1, and then 1, 2, and then 2. Okay, so it goes in like numerical sequence. I forgot what that's called, numerical sequencers. So 1, and that's a female. So 10, 11, 12. So 10, it says, is female, got that right. 11 is a female, got that right. And 12 is a male, got that right. 2 is actually, it says a female. I think that's a male. I'm going to go on the limb and say that's a male. This is female. This is image 3 is female. Image 4, it says this is a female. I would question that. I think maybe the model made a mistake. It'd say number 4 is female. I don't think so. Anyways, let's continue on. By female, 6 female. I think this is a female. It could go either way. Okay. Okay, no comment about that. 7 female, 8 female. I think that's a guy. And 9 says female. I don't think that is a guy. I mean, I don't think that is a female, but I don't know. I think the first CNN was a little bit more accurate. This ANN is giving me some feedback that I would question. But again, we're just using one model. This is, where is it? Optimizer's Adam. And what are we doing? Loss accuracy and binary classification for gender. So this is a model we're using. There's all kinds of models. There's dozens out there. I just picked this, I threw it in there. I did the analysis yesterday. I was late at night, so I went to bed, woke up today, and started this video that I'm talking to you right now. So maybe if I had to do this over, I'd pick a different model. This one is performing better than 50%, maybe 60, 70%, but I did see a couple mistakes. This last one is a little bit kind of sticking with me here. That is not a female. Number 9 is not a female. That is a dude that looks kind of like a bit like Brad Pitt, Chris Hemsworth a little bit. Guessing here, but I think that's actually like a non-celebrity. So anyways, that's how an ANN works. I think there's a little bit of room for improvement. If I went back and did that again, I would pick a different model over here, plug that in. But that would be a good exercise for you guys to try. I will leave it to you to handle that. You can plug in another model and see what you get for that. So here is the fourth and final analysis. This is a GNN graph neural network, and these are great for looking at any kind of network like Facebook, yourself or your friends of friends, your friends of friends of friends, or LinkedIn, or your connections, LinkedIn, and your connections, and your connections. So graph analysis is great for that. And we'll see how that works. So I am pulling in some stock ticker data right here. Again, the adjusted close price and the date, and the prices for all these tickers is probably 30. I think this is the Dow 30 components for 6 months back in time. So I'm going to pull this in, create a data frame, look at the returns and volatility. So the returns are basically the percentage change of the mean times 252, because it's 252 trading days a year, minus the weekends, minus all the holidays. There's about 11 holidays in the United States. So of 365 days, you have about 252 trading days. So you annualize that, you have your volatility, which is the percentage change times the standard deviation. So you have this right here, times the standard deviation, times the square root of 252, right, to annualize that. So if you don't know about finance, that's okay. Just take my word, this is how it works. And I have several videos on my channel about finance if you want to get into financial analysis or time series analysis or predicting stock prices, or is a stock correctly valued or overvalued or undervalued, and therefore it's a good investment opportunity. I have a bunch of videos on that, so check it out. We're not going to talk about that right now. Continuing on, we have the returns, the ticker, and the price. I just realized this is a mistake right here. That's not the price. All we need is the ticker, the returns, and the volatility. So ignore the first column for now. So go down here. The PyViz network allows us to do network analysis of all of these stocks. We're looking at the I and the J components and the correlation of all these stocks. And this is pretty cool. This actually generates a dynamic interactive chart that we can move to see which different stocks are clustered together. So here we see, if I zoom in, Coca-Cola, J&J, and Procter & Gamble. So these three are mostly similar. That's why they're clustered together. This is Boeing, Verizon, Honeywell. What's this down here? United Healthcare. All these stocks actually go into their own separate clusters, except for this group right here. This actually goes into one big cluster. So all these stocks are substantially similar, but all these other stocks, including McDonald's, Home Depot, Walmart, are different, right? So these happen to be clustered together. You moved around. It's kind of like jiggling around. It's kind of fun to play with. But just remember, this is a cluster of stocks that are mostly similar. These three are kind of similar, and all these others are similar only to themselves, right? So they are heterogeneous. These are all somewhat homogeneous because they're clustered together. So we need this network to understand the relationships based on returns and volatility of these stocks. That's what we're looking at. Okay, we're creating two dimensions, the horizontal and the vertical, right? So horizontal this way, vertical this way. This is the I and the J, the correlations. We're getting the columns and then the index of each, and creating the edges of these index, and then the tensors, okay, the labels, and then the weights of all these tensors. So again, the tensor is like the numerical representation of the stock. So you have to take it and chunk it and create a tensor for each stock and the return and the volatility, right, for each ticker. And once we have that, we can go ahead and put that into this custom layer algorithm and the GNN model to go ahead and model what these tensors are doing. Okay, so we'll skip down here for a minute and we get the actual GNN model right here. Again, neural network model. So we have the CNN, the RNN, the ANN. This is the fourth type. This is the GNN. Here's all the tensors. And then let me cut this out. I was experimenting with that. I'm actually not using that. I'm not using this one. And then we train the GNN model. So the model is set up. We can go ahead and train it right here. Okay, we see the epoch. This is the number of iterations. We go, I think 20. This is the first epoch. So we go 20 iterations. Number 2 is 21, 41, 61, so on and so forth, up to 181. We get to, I think, 200 different iterations. So remember, epoch is an iteration or one loop. Then we can evaluate the model. We have the predicted values based on all the tensors from above, and then the actual values, or actual volatility, sorry, not the predicted values, predicted volatility of the stock. So volatility is how much up and down the stock is going to move in that given period of time. Remember, 6 months back. So going back as time 6 months, we have the predicted volatility, then we measure it against the actual volatility, and we're going to see how accurate those predictions are. Okay, I can cut that out. I'm not using that. And then we have predicted versus actual. And here's the final regression plot. So here's the actual volatility on the horizontal axis, 0.15 to 0.3, predicted volatility, 0.15 to 0.3, vertical rate. The predicted perfect prediction is right here, the horizontal line. If I click on it, it actually disappears. If I click on the blue, that disappears. So these Plotly charts, this is actually Plotly right here, Plotly Go. It's very interactive. You can zoom in, you can zoom out. If you want to zoom in to get more details about that, that's fine. Double click to zoom out. So the goodness of fit shows you how close all these blue dots lie on the diagonal line. The diagonal line is the best fit line, and we look at the deviation from the line, and the closer the fit of all these dots to the line, the better predictions we were able to make. if it's dispersed kind of far away from the line, like it looks like it's kind of far, but it's actually not. It's only 0.2, 0.3. So if you look at here, it's 0.2, right? And then go over here to over here is 0.3. It's only 10% change, horizontal and diagonal. So it's not a big change. It's only 10% from most of the chart, maybe 20% for the entire thing. So everything is about within 20%, 15 minus 0.3. This is 0.3 minus 0.15. It's only 15% vertical. And again, horizontal, this is maybe 0.4 minus 0.15, so 0.25, 0.2 horizontal change. So it's not huge. But again, the better the blue lines line up with the red diagonal line, the better the fit, the better predictions we can make. So overall, the fit is decent. It's probably about 70%. I actually didn't calculate the R squared here. Probably should have done that. I've got a lot of other videos on R squared. Most of them I do that. So this time, I guess it just slipped my mind. I didn't do it. But overall, the goodness of fit, I would say, is about 70 to 75%. It's decent. It's statistically significant. We can live with it. We can work with that. I thought, okay, goodness of fit. If it was lower, like 0.5 or 0.6, it'd be kind of useless. We would have to pick another model or get more data to work with to make better predictions over time. Okay, we only have 6 months. It's a good start. I think it's sufficient in this case. Probably could go back more in time and get more data. You certainly could. Is it going to make for a better analysis? I don't know. That's debatable. You have to kind of consider the trade-off between the time to compute the results and for the model to converge and produce some type of result for you, and the accuracy of the results, right? If you get slightly more accurate results and you spend 10 to 12 hours doing the computations, is it really worth it for 1 or 2% increase in predictability? No, it's probably not. If you can spend another 5 minutes and gain 30 or 40% improvement in accuracy, then it's definitely worth it, right? So is it going to be a trade-off between computational time and accuracy or overall predictive capabilities of the model? That's what we're looking at. So we touched on 4 very interesting neural network models: CNN, RNN, ANN, and GNN, right? I told you, I have my notes here. It tells you which model is appropriate for which type of experiment or which type of use case, right? So you can go ahead and read the notes here: the data type structure, primary use sharing, and then temporal handling, any kind of like gotchas or best use cases or what these are designed for, so on and so forth. So that's pretty much it. I'm going to wrap it up right here. Thanks for your time today, and I look forward to seeing you guys in the next video. Thanks, guys. See ya.